it can be decomposed as it seems to be 3 different shapes. Sometimes they will give you those shapes, so that makes your life easy. Sometimes they won't, so you just pick them. So you realize, okay, you can decompose this into 3 different shapes. The left one is a semicircle, the middle one is a rectangle, the right one is a right angle triangle. In this case, they're giving you the correct system and they're putting the origin right here. Again, if you like it, you use it. If it's not there, you pick one that you like. And if it's there and you don't like it, pick another one. Just make sure you show it to me so that I can look at your work and refer to your and your free body diagram. Okay, let's imagine that the radius of this is 5. This is going to be C, so it's 4. And this is going to be 2 times 5, obviously. And that is going to be 6. Okay, so let's do X bar. We have 3 shapes. 1, 2, 3. This is a Riemann sum, therefore we add x1a1 plus x2a2 plus x3a3 divided by a1 plus a2 plus a3. Now you know that y bar will use the same denominator, so the same areas. So usually people make a table. A1, A2, A3, X1, and those are centroid, X2, X3, and then they're going to do the same thing with Y1, Y2, Y3. So that if they goof as they integrate all this into their ratio, at least they get partial credits. The very important aspect is this is under every term. Okay? You cannot break it up that way. Everybody has to be on the same denominator and numerator. Okay, so what is the area of a semicircle of radius 5? That is, what is A1? I will also assume that you know how to calculate area of those simple shapes. Rectangle, triangle, right angle triangle, circle, and semicircle. Can anybody give me either the functional form or the actual value of the area of a semicircle whose radius is 5? It is not a trick question. You've known this since you're probably 6 or 7. Yeah, pi r squared, and we divide by 2. Excellent. So pi is pi. R is 5, so 25 divided by 2. Bang. One done. What is the area of object 2, which is a rectangle? Yeah, 2 times 4. Excellent. What is the area of the right angle triangle? Or area 3? Here, be careful. Yeah, the general formula is 1/2 pH. But in this case, what is it going to be? Remember that this is 5, therefore this is 5, this is 5, and this is 5. Therefore, as we apply Tyson's formula for the area of a right angle triangle, what is the number we're going to get? Please give me a numerical value. Excellent. It's 2 times 5 times 6 divided by 2. Or 5 plus 5 times 6 divided by 2. Perfect. All right. Now, let's start with the easy guy. X2 bar. Where is the centroid of area? Oh, why is 2 and 8? Uh-oh. Uh-oh. Where, Tim? Where did I goof? Do you mean, oh, why is area 2, 8? I don't know. Oh, yeah. Thank you. My mistake, my mistake. I misled everybody. Hang on. This is area 2, area 3, area 1. This 2 is not a distance. Thank you, thank you. My mistake. So we would do the same. 5 plus 5 times 4. Is that better? Yeah, but it was my mistake. But that stupid 2 was misleading. Woohoo! Thank you, thank you. So 25, 40, 40. Perfect. Thank you, thank you, thank you. Okay, where is the centroid x2 bar? And remember, x2 bar must be measured from the y-axis. This is the source of all the problems, but they can be minimized greatly by just drawing it. x2 bar is the centroid of area 2 as measured from your x-axis, or as your y-axis. Therefore, let's draw it. This is the centroid of your rectangle. x2 bar is from here to here. Do you want to update your answer, Tyson? Yeah. Do everybody agree? And we go right, therefore positive 2. So far, so good? Okay. Now, can you give me x1 bar? Where is the centroid of area 1 with respect to the y-axis? Almost. Remember, it's a semicircle. That's where I give you this guy over here. That's the formula, right? Almost. So Tyson has half of the answer correct, the other half incorrect, and Tim has the other half correct, but he forgot the other half. Can we combine your 2 solutions to have one perfect? We're measuring that x1 bar from the y-axis, and area 1 is on the left side. Yeah, excellent. Oh, yo, 20. Okay, area 1, left side of the y-axis. Remember, we measure all the x bar from the y. So again, if you drew it, then you know, hey, my little vector is going left, same as chapter 2, minus sign. Okay, now last one, x3 bar. The key is going to be to draw it and to remember that all the x bar are measured from the y-axis, like that. That's x3. It starts here and go all the way here. So now that we visualize it, can you give me its functional form? And remember, for a right angle triangle, if you measure from the base, it's 1/3. If you measure from the tip, it's 2/3 the length. Tyson suggests 13/3. Do we all agree? I have no idea. Sounds complicated, but it could be. 6. That's pretty close. Well, almost. How did you get 6? Like that? Do we all agree with Ray? Remember that green arrow? Yeah, okay. Similar. Thank you, John. So we have to spam that hole, which is 4. And then we have to calculate this distance right here. And this distance is 1/3 of the length, 1/3 of 6. So we have to go 4 plus 1/3 of 6. Does it make sense, everybody? Tyson as well? When we draw it. Perfect. So again, this is the main source of problems. Oh, but that makes sense now? Better sense? Perfect, perfect. So please trust me. This is where 90% of the mistakes show up. And then we're going to see the other 10% later on. It's just by measuring. People forget that all the X bar are measured from the Y-axis. And same as in chapter 2, you go towards the right side of the Y-axis, it's positive. You go to the left side of the Y-axis, it's negative. And similarly, all your Y bar are measured from the X-axis. If you go up, positive. If you go down, negative. So one of the best strategies I've seen to allow students or anybody in general to avoid mistakes is to actually draw your vectors, because then you don't forget, oh, I need to add that stupid 4 because I'm measuring everything from the Y. Good. What about Y1 bar? Take your time. Remember, we're measuring everything now from the X-axis, and we're looking for the value or the position of the centroid of the semicircle. And your X-axis is at the bottom, it's right here. Let's draw it. This is what we want. Excellent. Yeah, just 5. Or R. Perfect. Y2 bar. That's trivial. Same. Excellent. And then Y3 bar. This time we're measuring from the X. Is the X located at the tip or at the base of that stupid right angle triangle? That means, do we have to go 1/3 or 2/3? Excellent. 1/3. And what is the length? 5 + 5. Excellent. Therefore, 10/3. Positive. Okay? So it's really just bookkeeping, nothing else. So as you can see, we've seen one case of a negative sign that may show up. Obviously, now you realize that if your coordinate system was here, all your Y bar will be negative, and 2 of your X bar will be negative. So you may show up and pick up negative signs. Only in the bar, guys. A are always positive, but it may be possible that you end up with negative sign in those guys. Therefore, you may have negative sign on the numerator, but so far, never in a denominator, because you just add areas, and areas are always positive. Good. Now let's look at a case where we may have an additional source of negative sign. Let's imagine same shape. This is 5, this is 4, this is 6. That means this is also 5. But I'm taking out this area out. So really, I just want this. You have different options. You can represent this as area 1, area 2, area 3, area 4. So far, so good? If you do this, and where's the current system? It was right here. Then again, the only negative one will be the X component of 1. This is going to be the only one that will be negative. Everything else will be positive, and all the areas will be positive. Do we all agree with this? Okay. second option. You consider this still to be 1, but you're going to consider this to be 2, same as last time. This 3, and you're going to consider this shape that you're taking out as one shape by itself. So you're going to take it out of there. It means that you're going to have the exact same amount of term and sign as what we just did here. This doesn't change, but you're going to add a fourth one. And since it's an area that you're taking out, in this formula, either you put the negative sign here, which is a little bit bizarre, so usually we don't, but in your application of this is going to be x1a1 plus x2a2 plus x3a3, same as before, but now you're going to neglect or take out x4a4 because you're taking out that area, which means at the bottom you're going to have a1 plus a2 plus a3 minus a4. So this new source of negative sign comes because you've taken out area. So if you decide to take out area, then you need to add the negative sign right here. Okay? On both numerator and denominator. So now you're guessing where I'm going with this. It means that if you decide to put your coordinate system right here, let's focus on this term. You have the negative sign because you took out the area, but look, this is x4 bar, which is located at -1. So now this one is also negative. Therefore, you're going to multiply two negative signs and they're going to become positive. Okay? So you have two sources of negative sign and they may combine with each other to turn the whole term back to positive. The first source of negative sign is just the x bar and y bar, depending whether you go left or you go down. So it's just chapter 2 issue. You may also pick up additional negative signs if you decide to take out area instead of only adding them. For every area that you take out, you have to have a negative sign in front of each. So this negative sign is usually associated with the area. So if you have a negative sign associated with the area because you took out an area, and that area happens to be on the left side of your axis or below your x-axis, then you pick up another negative sign for your x bar or your y bar, which means that mathematically, boing, they're going to become positive. That's perfectly fine.